This is the second lecture in Fourier series, part of ECE 343. Last time we introduced Fourier's big idea, which was that any periodic signal could be represented as a sum of harmonically related sinusoids. Before we can get and derive that so-called Fourier series, we do need to develop some mathematics. We started that process last time when I introduced the Cartesian coordinate analogy of estimating some object. So just a brief recap of that. Suppose that we have some object in the Cartesian plane, that's x, shown here, and we can represent that as a vector. It has some horizontal component and some vertical component, and we want to estimate that object as a linear combination of building blocks. In our particular case, we're going to look at a single building block, that's our phi. And so we are going to allow ourselves a scaled version of that phi, so c times phi, to create an estimate of our object of interest, an estimate of our x. In this particular case, because phi does not align in the same direction as x, phi isn't enough by itself to perfectly represent x. We know there's going to be some error, and that error is shown as the red line. To find the best coefficient c, we used what was called the orthogonality principle. So we were interested in this estimate, x hat being equal to c phi. We wanted to find that value c in the best way possible. The best way possible that we looked at last time was to minimize the size of the error. And the way we minimize the size of the error is we made that error orthogonal to, or at right angles to, the building blocks, to the phi. And so that's shown here graphically, that we have that error vector, which is the red vector going along straight up in this case, and it is at a right angle to the phi, so we get this nice right angle in there. And that guarantees that the length or the size of that error is as small as possible. We went through some mathematical derivation on that, and we found out that we could compute that optimal value of c, that one that resulted in orthogonality between the error and the building blocks, the phis, by taking the projection of x down into the phi. That's done with a dot product, so x dot phi. And then we needed to divide by the size of the building block squared, so divide by the norm of phi squared. If we choose c in this particular way, this is just a single building block case, but if we choose our phi in this way, according to the orthogonality principle, we minimize the error, right, that is generated by that estimate. And that's a good way of trying to come up with a good estimate. So we might ask ourselves, how do we use these ideas for signals? We've done this now for Cartesian coordinate vector case, but we in this class are interested in signals, functions of time, some sort of x of t. Is there something along the lines of being able to estimate functions using building block functions, and then finding the best coefficients to weight those building block functions so that the overall error between our estimate and the function of interest is minimized, that the error is made small? And the answer is absolutely. It's going to follow exactly the same principle, but we do need to develop some additional math in order to see that. So the answer, of course, yes, we can do that, but we need some additional math help. That's really the focus of today's lecture. We're going to do an introduction to linear vector spaces, what are called linear vector spaces. It's just taking a look at some mathematics, a framework of mathematics that's going to be useful in us being able to deal with this estimation problem in a very smart way. And then we're going to go ahead and formalize that orthogonality principle from the context of linear vector spaces, from this perspective of linear vector spaces, so that we can apply it to what we want, which is the estimation of signals. So in the class Blackboard site, there is some handouts, and there's a handout for the final exam as well. And part of that handout has a single page, which is double columned. One column is about linear vector spaces, and one column is about the orthogonality principle. I'm going to switch over to a different application, and we're just going to go through that handout. It's something that you get to use on the next exam, and it's something that you should be referring to frequently over the course of the next couple of weeks in working through this material. We're just going to go through that as we can. So let me go over and jump over to that. So in this particular case, I'm in that reader that allows me to take a look at this handout, and I'm on this part that is the column labeled linear vector spaces. So we'd like to talk a little bit about what is a linear vector space and what does it do for us. A linear vector space, and I'm just going to notate that with some kind of fancy or script X, is really just a collection of objects, a set of elements called vectors. And there needs to be two operations defined to make this linear vector space. Linearity, we've seen that term used before. Linearity as an idea is one that supports superposition. So we got to be able to do things like add, and we have to be able to do scalar multiplication. So superposition as a linearity property, or this idea of a linear vector space, that linear part really involves always those same two pieces, addition and scalar multiplication. So when I talk about linear vector spaces as a mathematical topic, linear vector spaces is a collection of objects, something called vectors, where we have two operations. One is the operation of addition. So if I have an element x or a vector x and another vector y that are part of that E looking symbol is an element of our linear vector space x. There has to be an operation plus, right, where I can take that first vector x and add to it the vector y. And that should also be part of my universe, part of this set of elements that makes up this linear vector space. So that should also be part of script x. That addition, if you think back to what we were dealing with in the Cartesian plane, could be done pretty directly. I could have a vector x, right? And I could have a vector y, and we know how to add these guys together. I would just put them head to tail, right? And then once I put them head to tail, I could just add them together, something along those lines. Scalar multiplication is something similar. We've seen a version of multiplication before, scalar multiplication before. We're going to just look at it in this way, that if I have a vector x that's part of my linear vector space, that's this piece right here, right? And then I could talk about some complex constant, let's call it alpha, then I should be able to multiply my vector by alpha, and that should also stay in my universe of objects in that linear vector space. We know how to multiply numbers. If I take 3, right, times a vector, right, we know that that just makes its magnitude 3 times bigger. If I take minus 3 times something, right, not only does its magnitude get bigger, but its direction reverses because of that minus sign. We've seen all sorts of cases of just taking something and multiplying it by a scale factor. These aren't too difficult. So, linear vector space, collection of objects that have the operations of addition and scalar multiplication. These two operations need to satisfy the following properties also for us to have this thing called the linear vector space. Really what this is this is a statement of stuff that you've seen in mathematics before, and it's really just going to confirm that those operations that you've come to know and love are going to be available to you and that you can use them without any kind of worries about making things go bad. Not every form of addition or every form of scalar multiplication would satisfy all of these properties, and so that would not be part of a linear vector space. But for a linear vector space, we need the following properties to be held. There needs to be a commutative law of addition. What that says, commute means to move, right? So commutative law means that whether I add x to y or y to x, I should get the same result. The order, commute means move, so the order of addition, whether I do x with y or y with x, should not make a difference in the result. This is stuff we've seen from algebra for years in your education. In fact, if you look at the set of real numbers and the algebras that we deal with, that is part of a linear vector space. There's an associative law. Associate just tells us how we group, right? So an associative law says something like this, that if I add x and y, group that first, and then add to that the vector z, that would not give us any different answer than if I grouped, let's say, y and z first, and then added to that x. The grouping order here should not matter either. Again, these are kinds of operations that are second nature to us. It's stuff that we have seen before. None of these should be a surprise. There is something called an additive identity. The additive identity property for linear vector spaces says there exists, so that's that backwards E, that's red, there exists some theta. I'm going to call theta my fancy zero, more on that in a second. There exists theta that is part of our universe, part of our linear vector space, such that if I add that theta to x, I end up right back at x, okay? So why do I call it a fancy zero and why don't I just use a zero? Well, let's go back over again to our vector kind of analogy. I could have some object, some vector sitting out there. That could be this point, and I could call that, oh, let's not call it W, let's call that guy X, something like that. I need to be able to add something to that X, right, so that I don't move. Well, what do I add to some coordinate pair, some horizontal and some vertical? I don't add just a single zero. I add 0 in the horizontal and I add 0 in the vertical. So here my theta might be equal to the pair of zeros, 0, 0, because I'm talking a two-dimensional object. I'm talking about something in the coordinate plane. So that's that theta. This theta being a 0, right? It's a fancy 0. It might not just be a scale value. It might be a pair of values or a triplet of values or a whole line of zeros. In fact, as we move on to this idea of signals, you might think of what can I add to a signal that returns me back to that signal? It's not just a single point of 0, but it's a 0 for all times, right? So that would be our fancy 0 in that case. We get some other kinds of properties that you would expect. So for example, if I have that scale factor alpha and I multiply it by a group sum x plus y, I can distribute that across and get alpha x plus alpha times y. So just a way of distributing scale multiplication. I can also take a sum of scales. So let alpha and beta both be complex numbers, add them together, multiply them by my vector x. I should be able to distribute that as well and get an alpha x plus beta x. These seem algebraically sensible. It's stuff we've seen before and really should not be a particular surprise. Here's a different way of defining that theta, that fancy 0 that we had used before in property 3. If I take the scale value 0 and multiply it by my vector x, I should get that fancy 0 because 0 times anything, right, gives me that additive identity, that fancy 0. In a similar way, we get a multiplicative identity, and that's just a constant of 1, right? So 1 times x also equals x. My expectation is that no one should have any particular problems with these properties because they are all properties that we typically use in the math that we see day to day as engineers, as people. Okay, so we're going to continue. So we have this idea of a linear vector space. It's a collection of objects. There's some operations defined on that collection of objects, notably summation and scalar multiplication. We have some rules or properties that guide us in those operations, and those are ones that are familiar. Linear vector spaces also support this idea of something called an inner product. So let's define this idea of an inner product. Inner products are not unique. You could define many inner products for a particular linear vector space. So they don't need to be unique. But in a general sense, we are going to notate this idea of an inner product using angle brackets. So when I take a look at this expression that I've written here, where it says left angle bracket x comma y, and then there's a right angle bracket, what we're going to read that as is you would say that says the inner product of x and y. So we are going to be looking at something that we will define, some operation called an inner product. We'll denote it as angle bracket x comma y, and then undo the angle bracket. And what comes out of that operation? It's a complex number, or at least a potentially complex number. It could also be real. Reals are just a subset of complexes. So in general, it's a complex number. And it's defined, right, on the cross product between two vector spaces, x crossed with x, meaning that I have a vector that's part of my linear vector space, x, right, and I have another vector, y, that's also part of a vector space, x, and this cross or this inner product is defined on this element x interacting with this other element x. Okay, so what does this inner product need to be a valid inner product? Frankly, there are classes that spend entire semesters talking about things like linear vector spaces. So clearly we are doing the abbreviated version here. We're not going to be proving all of these. We're not going to be able to dig in them deeply. We are going to simply use the results of mathematicians and say, yes, there's this thing called linear vector space. Yes, there's this thing that it supports addition and scale multiplication. Yes, it has a bunch of properties that actually look really common and simple and obvious, or at least familiar to us. And there is an operation that we can define on these linear vector spaces called an inner product. To be a valid inner product, 4 properties have to hold. The first is that the inner product of x with y needs to be equal to the inner product of y with x complex conjugated. So this is a sort of commutation property, if you will, that I interchange the order of the arguments of the inner product. I don't see anything other than a conjugate difference, right, in doing that interchanged order. So however I define my inner product, the inner product of x with y needs to be equal to the inner product of y with x complex conjugated. The second property that has to be held is that if I take 2 vectors, x and y, and I add them together and then inner product them with z. So this would be read the inner product of x plus y with z. I should be able to distribute that in a sense to make that as the inner product of x with z, and then add to that the inner product with y and z. The third property we need is that if I scale multiply x before inner producting it with y, I should be able to pull that scale factor alpha out and just multiply it by the inner product between x and y. So the inner product of alpha x with y should be equal to alpha times the inner product of x with y. The last property we need for a valid inner product definition is that if I take the inner product of x with itself, okay, I need to get not only a scalar out, but it has to be a real and positive scalar. So inner product of x with itself has to be greater than or equal to 0. And the only way it actually equals 0 is if x itself was at that theta we talked about, that fancy 0. We will find out very shortly that this inner product of something with itself is really like a norm square kind of an idea. And so if you think of most of the examples you've seen of something norm squared, it's always a non-negative quantity. And the only way you get something with a size, that's what a norm is, a size equaling to 0 is if the thing you were looking at was a 0. If I have an inner product, now I can start talking about this idea of orthogonality. Orthogonality is a generalization of that 90-degree angle between two objects that we saw in the Cartesian plane. It is more general than that because now we are going to be able to talk about orthogonality of stuff that it doesn't look like a geometric 90 degrees. Orthogonality is really just saying that the inner product of two things is equal to 0. So orthogonal, you can also call these perpendicular elements. If I have orthogonal elements x and y, okay, that are part of this linear vector space x, the way we know they are orthogonal is if, according to a particular inner product, the inner product of x and y gives us this scale value of 0. We can also denote that, right, as x perp y. So use that perpendicular, that upside down T symbol. That says the same thing. X is perpendicular to, or x is orthogonal to y. So with an inner product, right, we can get a sense of things being orthogonal by just knowing that the inner product is 0. What that tells us is that by that particular definition of inner product, the projection of one onto the other has nothing in common, right? We had seen this idea of a dot product back in our Cartesian plane. Dot products are kind of like a geometric version of what an inner product is going to give us, okay? Inner products and dot products are tightly connected. Inner products are a generalization or a more general form of that dot product that we saw in our last lecture's examples. We'll pull all of this together, of course. We're just right now laying out the math that is going to help us. So still in this linear vector space, we can talk about the norm of a vector x. We designate that with two vertical lines on either side of the vector. So the norm of x on a linear vector space x satisfies a couple properties itself. The norm of any vector has to be a non-negative real constant, right? So norm x has to be greater than or equal to 0, and it's only equal to 0 if x is the fancy 0. It has to satisfy the triangle inequality, which is that the norm of or the size of a sum of things has to be less than or equal to the sum of the sides. We can get a nice geometric interpretation for this using things like a Cartesian plane. And then the last one is that the norm of alpha times x is just the absolute value of alpha times the norm of x. So we should be able to pull that alpha out and just scale the norm of x by the absolute value of alpha. Okay, so that's a way of getting norms. It's a way of telling us the size of a vector. The way we compute or determine a size is based on a particular inner product definition. And what this also tells us, if you wanted to dig deeply on this, is that for a particular linear vector space, and we'll look at some examples here in a minute, for a particular linear vector space, because we could have multiple inner products defined on that, we could also support the idea of multiple different sizes, multiple different norms. Not everything in a linear vector space, just because I have a vector x, doesn't mean its size is fixed. Its size depends on whatever inner product definition I've adopted. Well, one of the things that we'll note is that the square root of the inner product of x with itself is a valid norm. That is, the inner product of x with itself really does satisfy the idea of the norm of x squared. Okay, so let's briefly come up with an example that is something that we should all be able to appreciate, having spent some time not only in this class but also in previous classes and previous math classes as well, of something that fits into this model of a linear vector space. Just a very quick recap. Why are we doing this linear vector space? It's a mathematical construct, if you will, that just allows us to move forward in a really certain and sure way. It provides us the structure of the mathematics so that we can move forward and get particular results that we will know what they mean and how to proceed. So, an example, the set of all continuous time energy signals is a linear vector space. What does that mean? That means that there's this universe of objects of interest, and those objects of interest are going to be continuous time energy signals. We already saw or studied in this class before things that were a continuous time energy signal. So, for example, I could sit there and do something like this. I could draw a signal that was just like a little 0 to 1 height 1 pulse, right? That is a continuous time energy signal. If I take a look at it, it's certainly a continuous time signal. If I compute its energy, the energy is finite, so that is an example of a continuous time energy signal. I could do a little ramp function that was defined 0 to 1 and had a peak height of 1. That's also a continuous time energy signal. I could dream up a bunch of these guys. I could take a half of a sine wave, right, between 0 and 3 if you wanted to, and have its peak height be 4, something along those lines. That is also a continuous time energy signal. There is an uncountably infinite number of signals that fit into this general category of continuous time energy signals. The statement here is that the set of all of those guys, all continuous time energy signals, forms a linear vector space. What does that mean? That means that for those continuous time energy signals, we should be able to define two basic operations, one of addition and one of scalar multiplication. Let me go ahead and re-erase part of this here, and I'm just going to go and think about how would I add, for example, those two guys together. Well, this is old time kind of stuff that we had seen before. We just point by point add them, and I would end up getting a signal a bit like this. It would just be that one kind of square or rectangular function added with that triangle function, and I'd get kind of a little bit of a DC offset ramp function. We know how to add energy signals, so we certainly have an addition operation. And guess what? The addition of those two signals is still an energy signal. There's no way for it not to be an energy signal. That's closure under addition. I add two signals together that are part of this linear vector space of continuous time energy signals, and I still end up with a signal that is a continuous time energy signal. I could also scale multiply these guys. If I took the second signal there, let's call that guy x2, and if I did 3 times x2, what would that mean? Well, I scale that guy so that its amplitude gets bigger, right? It's going to get everything scaled by a factor 3. Each point as a value of t is going to get multiplied by that scale factor of 3. So we have a lot of experience in doing things like adding signals together and scale multiplying signals. Those are things that are obvious. So set of continuous time energy signals forms a linear vector space. We know that there's this operation of addition, pointwise or point by point addition, and we know that there's something called scale multiplication. Furthermore, if I went back up and I looked at all the different properties on this, does it matter which order I added those signals up together? Let's make that something other than black. Let's make it orange for now. Would it matter which order I added those signals? Absolutely not. We know that we could add x and y or y and x and I'd get the same thing. Does it matter how I group the additions when I add those continuous time energy signals? Absolutely not. I could group a signal x plus y and then add to it z, or I could have done y and z first and then added x. Is there some zero or fancy zero out there such that if I add it to x, I get x again? Sure, that's just a zero for all time. It would be a flat line right there at a height of 0. Can I scale a sum of signals and just do it as a scale of each of those signals then added? Absolutely. That's an easy one to check, as are all these other properties that we see in there. Every single one of these can be easily validated or verified as properties that hold for this set of all continuous time energy signals. Easy to show. that the set of all continuous time energy signals adhere to or follow these basic operations and also have those two operations of addition and scale multiplication that are necessary for defining a linear vector space. Where it gets more interesting is what happens when I want to define an inner product. Here is one inner product that I could define. I can define, in this particular case, an inner product of my signals. So I have a continuous time energy signal x. I have another continuous time energy signal y, and I'm going to define the inner product between x and y as the integral of x times the conjugate of y, and then just add up all that content, so integrated with respect to t. So is this a valid inner product definition? What are the requirements for inner products? The inner product of x with y has to be equal to the inner product of y with x complex conjugated. Well, let's take that right-hand side in this case. The right-hand side would be an integral. I'm going to make this pen quite a bit smaller, and I'm going to do it in black. And let's go back and try this again. So I would have the inner product, if I was going to look at this right-hand side, I'd have the inner product of y of t, and then I have x conjugate, that was just by our definition of t, dt, and then I'm going to take that whole thing conjugated. Well, if I conjugate a sum, I can bring that conjugate inside past the integral. This is integral with respect to a real variable. Conjugate doesn't affect the integral, and I'm going to get that being then the integral of y conjugate, and then I'm going to have x complex conjugate conjugated again. That just gives me x of t dt. And that, of course, is equal to the inner product of x with y, which is what I needed to show in this case. I can easily show that this proposed definition for inner product between y and x, or between x and y, the inner product of x with y being equal to the integral of x times conjugate y, satisfies this first property. In the same sort of way, I can easily show this second property as well. That would be an integral of what? I would have x plus y, I'm going to leave the t's off here, and then I would have z conjugate. But integration is a linear operator. So this is an integral of xz. Let's try that one again. So that's an xz conjugate plus an integral of yz conjugate, right? Which is inner product of x with z plus inner product of y with z, something along those lines. So we showed that that second one is also true. The scale factor by alpha is almost too trivial to worry about. You put an alpha inside. Let me just do that in a different color, red. If I put an alpha in here, right, I could certainly pull that guy out. So that one's easy to show as well. The last one has to do with what happens if I took the inner product of x with itself. Well, what is the inner product of x with itself in this case? It's going to be an integral of x times x conjugate, right? Well, that's just the integral of the size, the absolute value of x squared, right, dt. So clearly that has to be greater than or equal to 0. And the only way it's equal to 0, the only way that that integral is going to give us nothing is if x itself, right, was 0 everywhere. So it is easy again in this set of all continuous time energy signals to show that not only was it a linear vector space, but we can define this very nice inner product between x and y. This inner product also has a nice advantage in that the norm associated with this, remember we said a norm of x can be gotten from the inner product of x with itself, that just returns the energy of the signal. If you notice, this whole thing was how we defined, if I used it with not a y there, if I let x equals y, right, I would get an x with x conjugate, that is equal to energy x. Right? So our inner product here also has some meaning. This inner product, which can help us get an idea of size if it's an inner product of something with itself, we're saying we're going to let that be consistent with our understanding of how we've defined energy. And energy is a way of looking at the size of a signal. Okay, so what have we done? We've got through this first column on this formula sheet, just giving us some mathematics that will hopefully be helpful to us as we go along. We've introduced this idea of a linear vector space. We've got a collection of objects for which we've got addition and scale multiplication. They have a bunch of properties that we've seen and known and used in math before, so we get to use all those things in the way that we've really come accustomed to. No worries about that. We've defined something called an inner product. That inner product has a few, mathematicians require a few properties to be a valid inner product. And once we have that inner product, we can start talking about not only the size of something through this idea of a norm. That's just the inner product of something with itself. But we can also talk about orthogonality. And that's this idea that an element X really has basically no projected part onto Y. This inner product is also connected to the dot product kind of an idea that we'd seen before, like a projection, projecting one onto another, that they have no overlapping content. And we looked at an example that was not so easy to see or visualize in terms of, like, let's say a Cartesian coordinate. We did this more in a signal type standpoint. We looked at the set of all continuous time energy signals. We saw that they were indeed linear vector spaces, and that we could also define an inner product that was consistent with the idea of energy. Okay, so that is the background mathematics that we need in order to move forward with our idea of estimating an object of interest using some building blocks. So let's move over to the second column of this formula sheet, the second column of the formula sheet. And I'm going to need to do a little bit of erasing on here so we don't get kind of distracted by all that other stuff. But let's go ahead and look at this second column of this sheet. This second column is labeled the orthogonality principle. So this one here, the orthogonality principle is just an idea, okay? The orthogonality is a principle or an idea that is going to help us when we try to estimate an object that is in a linear vector space using building blocks. And those building blocks, we know that the mathematical term for that, the better mathematical term, is something called a basis functions. So let's set up the basic idea. For right now, I'm just going to give the result, okay? So we're going to look at the orthogonality principle, and I'm going to say what is the problem, what is the result that orthogonality gives us. If you compare it to stuff that we saw in our previous lecture, you're going to see it looks familiar. And then later, another lecture from now, we are going to prove this guy. We will prove this. We will prove it. But for right now, that proof is a distraction. We just want to know what it does. So later, right, we will prove. For now, right, we just want to know, what does it mean? What is it? What is it? What does it mean? So let's read it through together. If I have a linear vector space, right, and I have an object in that linear vector space, called it X, that's my object of interest. So I have some universe and I have an object of interest in it. That universe, by the way, could be the Cartesian plane. The Cartesian plane is a linear vector space, and some point in that Cartesian plane could be an object of interest. That's something that we dealt with last time. And then I'm going to go ahead and give myself some set of functions, which I'm going to call phi sub k. And I'm going to let there be cap k of them. Cap k could be any, right, positive integer. So I could have 1 or 2 or 3 or infinite number of these basis vectors. So I have an object of interest X, and I've got a bunch of building blocks, the Lego pieces, if you will, these basis vectors. And what do I want to do? I want to estimate that object of interest with some estimate that is a linear combination of those building blocks. So my estimate, x hat, and we're going to subscript that k. Why do we subscript it k? Just because it's going to be a k-term approximation. So it's going to be a k-term approximation to the object of interest. And what it's using is it's using a bunch of basis function. Okay, those phi k's, they are known. We know what they are, right? There's no question about that. But we can scale the size according to some coefficients. The ck's, those are my unknowns. I don't know what they are, at least initially, for some particular object of interest. I know I want to estimate that object. I want to estimate it using a linear combination of building blocks, right? And I need to find out how big or what type or what size a building block. In each case, each of those building blocks gives me the best estimate. I think if you again think back a little bit when we first introduced the idea of Fourier and a little bit of an idea about where we might go with this, you can guess what our building blocks are going to be. Eventually, we're going to do something like this. The object of interest is our signal, right? And we're going to build it up with scaled versions of what kind of building blocks? Well, sinusoids, because sinusoids are convenient for the study of signals and systems. So this is a generalization that can help us in finding this approximation or this this representation of a signal using a sum of sinusoids. So that's where we're going eventually. So our estimate x hat k is just a linear combination of those k basis vectors. We want to find the k constants, that's the ck, little k going from 1 to cap k, and we want to do those in a smart way that it makes the error, right, the size of the error as small as possible. So I want to choose these c's, right? Choose the c's to minimize the size of the error, right? To minimize the size of the error. If I can make the error size small, well, then I must be doing a pretty good job in my approximation. Well, what is the size of anything? Well, that's where an idea of a norm comes. We know norm is one way of coming up with a number that is indicative of the size of some object, the vector. So I'm going to look at my error, that's x minus x hat k, and I'm going to take its norm squared, right, its size, which is represented in terms of an inner product. It's the inner product of the error, x minus x hat, with itself. So inner product of x minus x hat with x minus x hat. Well, it turns out, and this is where, again, we're not going to prove this just yet, but we will prove it later, the best choice does satisfy this idea of the orthogonality principle. This is just a gorgeous result. It's also what we saw last lecture when we said we were trying to find those coefficients, and we said the best coefficients made the error orthogonal to the data. It's the same thing going on here. It's just we're doing orthogonality in this generalized sense using inner products. So the best choice satisfies the orthogonality principle. The best choice of these coefficients, right, satisfies the orthogonality principle. And what is the orthogonality principle? The orthogonality principle is this, that the error must be orthogonal to the data used in the estimate, the fees. So the error, that's x minus x hat, right, needs to be orthogonal to the building blocks, and not just for one of them, but for all of them. So if I want to find the best C sub k's, and there's cap k of them, I need to make sure that the error is at right angles, orthogonal, perpendicular to the k, cap k, basis functions. I called them or subscripted them phi L just to avoid some confusion because we're going to get both L's and little k's coming up here. Okay, so what does this require? Orthogonality as an idea, that's this thing here, is represented using an inner product. So I'm going to go ahead and do that here. The inner product of the error, x minus x hat, with the basis function, phi sub L, that inner product has to be equal to 0. That is what orthogonality is defined as. And because we said it had to be true not just for one of the basis functions, but for all of them, we're going to get cap k equations that have to be satisfied. Well, what can I do with this? This is an inner product of a sum of two pieces with something else. Let's do a lateral move over here and look at inner product definitions. There was this inner product definition number 2 that said if I have an inner product of a sum of two things with another thing, we could just do it as a sum of two inner products. Well, I'm going to use that over here. So I have an inner product of x minus x hat k with phi L. What does that give me? Let's go ahead and do this in black again. So this is going to be equal to an inner product of x with phi L, right? And I'm going to have a minus an inner product of x hat with phi L, and they still have to be orthogonal, so it's equal to 0. Now I'm going to do what? I'm just going to take one of these terms, the minus inner product x hat with phi L, bring it to the other side. That gives me this expression. The inner product of x hat with phi L has to be equal to the inner product of x with phi L. And it doesn't have to be there just one time, right? It doesn't have to be there just for one of the basis functions. It has to be true for all of the basis functions. So that has to be true for L equals 1 to cap k. There are cap k equations at this point. This orthogonality principle, that the error has to be orthogonal to the data, results in a total of cap k constraints, cap k equations that I need to satisfy. Well, guess how many unknowns I have? I have cap k unknowns, the C sub k's. So the hope is, and what does happen, is that I should be able to solve these cap k equations and the cap k unknowns. I don't see yet the cap k unknowns, but I can get it by substituting in for this x hat sub cap k. What is x hat sub cap k? If I go up just a little bit, I see it's the sum, right, of scaled ck phi k's. So move my way back down here, and I put into this guy right here my sum of my ck right? Phi k's into there, and that's going to be a sum on little k going 1 to cap k. Now I have an inner product of a sum of stuff with phi L being equal to the inner product of x with phi L. Again, going laterally back over there, I know how to deal with the inner product of a sum of something with something else. It's a sum of inner products. So make this substitution, right, for x hat, and then use property number 2, and I can pull that summation outside. So I'm going to get a sum, little k going 1 to cap k, of the unknowns that I'm looking for, ck, and then I'm left with what? I'm left with this pk, that's this piece, inner product with this phi L, that's this piece. And it all has to still be equal to the right-hand side. That's the inner product of x with phi L, and it has to be true for all of the basis functions, L equaling 1 to k. So I get a total here of cap k equations and cap k unknowns. If I knew nothing else about my basis functions, this is where I'd have to go. This is what I would have to solve. There are cap k unknowns, right? Unknowns. And I have, quote, cap k equations. I have k equations and they're linear in the unknowns. I should be able to solve it. I could solve it with my favorite linear algebra approach. Well, that's fine. We could certainly do that. But there are occasions when this thing becomes even a little bit simpler. If my building blocks, right, those phi k's, are what are called an orthogonal set of basis vectors. What does that mean? That means the inner product between any of my two building blocks is equal to 0. In a more kind of intuitive way, this says that each building block adds completely new information. It completely explores a new part of my signal than what had come before. If the building blocks themselves are mutually orthogonal, that means every single building block that I bring into there, right, is equal to 0, okay, when the two building blocks are different, something interesting happens. If I go back here and I take a look, let me see if I can make this into a different color just to highlight what I'm looking at. I'm going to make it pink. If I look at this equation in here, I'm looking at the sum of ck times phi sub k with phi sub L. And I'm going to be running through all the values, right? L equaling 1, 2, 3, all the way up to k. So there's cap k equations in there. But my sum itself, the sum, right, goes k equaling 1 to cap k. For cap k minus 1 times, phi sub k is equal to something different than phi sub L. Only in one case would my little k be equal to the little l. So if I had mutually orthogonal pieces where phi k and phi L have an inner product equaling to 0, most of the terms in this sum, right, most of the terms in this sum are going to go to 0. The only case that wouldn't is when k equals L, I don't get, right, I don't get 0. That makes this whole sum drop down to a single term. And what do I end up with? I end up with, well, this is when k equals L, or L equals k, whichever one. I'm going to leave it as substituting L equaling k. So I'm going to get a ck inner product of phi k with phi k, because, right, k was equal to L, or L equaling k. And then that whole thing has to be equal to the stuff on the right. And that's going to be inner product of x with L was equal to k. So let's just put it all in terms of that one thing, pk. I can solve for my ck, right? It is going to be ck equals the inner product of x with phi k. That's the inner product of x with phi k. And then I have the inner product of phi k with phi k. Well, that's just the size of phi k squared, the norm of phi k squared, okay? So when we have orthogonal basis vectors, we can find each one of these coefficients individually and independently of the others. We don't have this matrix of equations. We can just solve them individually. The other way of looking at that is that the matrix that would come out of this thing would be diagonal. It would be a diagonal matrix coming off on the left-hand side, multiplying the unknown vector of c's. So we can solve for those guys individually. And oh yeah, this thing absolutely, right, should look familiar. That's exactly the form that we saw last lecture when we talked about estimating an object in the Cartesian plane, and that the coefficient of interest, right, was based on the dot product. That's just a special case of inner product over the size of my building block squared. It's exactly the same result, a generalization of what we had already seen for the Cartesian plane. For mutually orthogonal basis vectors pk, notice that each ck possesses that important finality property, which is to say that I can find the CKs, right, independent of any other coefficient. That means I can compute them each individually, and once I have them, they are not impacted by any of the other coefficients. There's a little last statement talking about what the actual error looks like in terms of those CKs. We don't have to worry too much about it. So what have we done up to this point? We have laid down the background information, some background mathematics necessary for us to start working on this estimation problem of estimating some signal using some building block or building pieces. We just noted that mathematics has this nice concept, this nice framework called linear vector spaces. Within that, embedded in that, is this idea of inner products by which we can understand concepts like orthogonality. And O, as long as you're willing to take my word for it today, we'll prove it later. This orthogonality principle, once we know what orthogonal means, this orthogonality principle tells us the best kind of coefficients to make up a linear combination estimate of an object of interest using some basis functions, some building blocks, some Lego pieces. And that's the thing that we are trying to do. That's the thing that we're going to ask or that Fourier asked sinusoids to do, or we can use this to derive Fourier's series kind of representation. Okay, so back to our regular lecture. Let's just take just a few minutes and see if we can provide a very short example of some of this using some actual numbers just to see how it might work. We had already noted before, right, that the set of all, so we have the set of all continuous time signals, was a linear vector space. I'm going to do the set of all continuous time energy signals on the interval 0 to 1 is a linear vector space, okay? Something like that. What does this mean? It means I'm going to have some energy signal that is defined from 0 to 1. We're not going to worry about what it is out of there. And by saying it's an energy signal, we just are saying that that guy's got, you square it and you integrate it, it's going to be a finite number. We can add these guys together, no problem. We can scale multiply them just like we've seen everything else before. I'm going to go ahead and define an inner product that's somewhat like the energy of signals that are defined on the interval 0 to 1. So I'm going to do the inner product of x and y is going to be an integral. I'm just going to have it not go from minus infinity to infinity. I'm just going to have it go 0 to 1 because I'm restricting myself to a particular interval. And I'm going to have x of t, y star of t, dt. This is very similar to the first example linear vector space that was given at the bottom of column 1 on our formula sheet. Okay, just I'm looking at the interval 0 to 1 instead of minus infinity to infinity. Okay, so I have a linear vector space and I have a definition of inner products. Let's take a look at a signal. I'm going to let this signal, again, it's going to be defined on that interval 0 to 1. It is as a function of t. This is going to be my signal x of t. And let's just let this guy be a linear function that decays from 1 down to 0 on that interval. So we could write that, parameterize that out. That's 1 minus t. So there's a signal like that. I'm also going to give myself some building blocks, some pieces that I'm going to try to use to estimate or approximate this signal. These guys, these pieces, these building blocks, my basis functions. I'm going to look at some basis functions that are consistent with what are called the Walsh basis functions. These are the Walsh basis functions. I'm not going to look at all of them. I'm only going to look at two. The first Walsh basis function looks like this. It is a constant one from 0 to 1. So my first building block just looks like a little DC signal on that interval 0 to 1. My second basis function for the Walsh basis functions, right, is going to look like a 1 for half and a minus 1 for the other half. So it's going to go 0 to 1. It's going to have a height 1 at first, and then it's going to have a height of minus 1 at the second half. And that transition point occurs at 1/2. Those are my two basis functions. So here's what I would like to do. I would like to estimate x, right, using two terms, right? And I would like to do that then as some constant c1 times my phi1 of t plus some constant c2 times phi2 of t. I know what phi1 is. I know what phi2 is. The only thing I don't know is I don't know what those coefficients c1 and c2 are. I do know what the signal is that I'm looking for, right? And as we said, we know the building blocks. We just need those coefficients. Well, some things that will help us in figuring this out. We could go back to that formula sheet and we could come up with our set of equations. And I'm just going to go ahead and write that out. It says something like this. It says a summation, and this is going to be a summation k equaling 1 up to the total number of terms. In this case, it's 2. And I have my c sub k's, and then I'm going to have the inner product of phi sub k with phi sub l. That needs to be equal to the inner product of x, right, with phi sub l, and that has to be true for L equaling 1 up to k, and our k here is 2, something like that. So there are 2 equations and 2 unknowns in this particular case. So let's go ahead and take a look at what these equations look like, okay? If I expand it out term by term, I would get something like this. I get C1 times the inner product of what? Phi1 with, let's look at the L equals 1 case first. So Phi1 plus C2 inner product of, we're going to have Phi2 with Phi1. That has to be equal to X inner product with phi sub 1. That is one equation. L equaling 2 equation looks something like this. I would get C1, and I would have an inner product of phi1 with now phi2 plus C2, phi2 inner product with phi2 being equal to X inner product with phi2. Okay, so my L equaling 1 and my L equaling 2 case. If I wanted to make this in a kind of vector sense, I could, or a matrix representation, I could do it like this. I could have the inner product of phi1 with phi1, the inner product of phi2 with phi1, then down on the next line, inner product of phi1 with phi2, and then lastly, the inner product of phi2 with phi2. This little matrix here is going to get multiplied by C1, C2, and that's whole thing going to be equal to what? It's going to be inner product of X with phi1 and inner product of X with phi2. Now you could solve this with your favorite linear algebra kind of package if you wanted to, so we could certainly do that. Just some notes on here. Because phi1 and phi2 are known, with a little calculation, we can figure out what the inner product of phi1 with phi1 is. We can figure out what the inner product of phi2 with phi1 is. We can figure out what the inner product of phi1 with phi2 is, and the same thing with the inner product of phi2 with phi2. We can, because we know the object we're trying to estimate, we can figure out the inner product of x with phi1 and x with phi2. The only thing that's unknown is that C1, C2. We could go through all those calculations, stuff them into this matrix, and then do the matrix inverse of that matrix on the left, and we could solve for the unknown coefficients C1 and C2. I would like to save just a little bit of effort, though, by noting some stuff. I want to look at the inner product of phi1 and phi2. What does that look like? Well, it's going to be an integral, because we said our inner product was the integral from 0 to 1 of phi1 of t times phi2 of t, and it probably could have had a complex conjugate. If I was being really careful there, I'm going to go ahead and do that because my fees were real. I guess I could have done without it, but let's go back and amend that for just a moment. Let's go, oh, and I did have it back there, so we do have that conjugate in there. Look at what my phi1 is. It's 1 over the entire interval 0 to 1. So phi1 times anything is just going to be the anything, right? So if I go back down here and look at phi1 inner product with phi2, this is going to be an inner product of 1 times phi2. That's just going to be an inner product of phi2 t dt, because phi2 is real, its conjugate is just equal to this signal. So 0 to 1. So this is the area of phi2. What did phi2 look like? It was a 1 for half the time, and it was a minus 1 for half the time. So that's an integral 0 to a half of 1 dt plus an integral of 1 half to 1 of minus 1 dt. And that, of course, is 0. It's got 0 area. What does this tell me? It tells me phi1 and phi2 are orthogonal, right? Their inner product being 0 makes them orthogonal. And I know that if my building blocks are orthogonal, I can find each of the coefficients individually. What did that tell me? Actually, it told me that this term here, phi1 and phi2 is 0, and phi2, phi1 is 0. Both of those guys are 0. Because I got just a diagonal matrix here, I should be able to solve for the C1, C2 without all that extra kind of linear algebra difficulty. So let's go ahead and think about that. C1 is going to be what then? It's the inner product of x with phi1, right, over the size of phi1 squared, which I can do as an inner product of phi1 with phi1. Well, what is the inner product of x with phi1? That is going to be an integral 0 to 1. What is x? It is 1 minus t. What is phi1? It's 1 on that interval, dt. Over, what is inner product of phi1 with phi1? That's going to be the integral 0 to 1 of phi1 is just 1 times 1. That's just going to be an integral of 1 dt. That, of course, is just equal to 1 in this particular case. So it turns out that phi1 also has size 1. We didn't even have to do that definition, that division of the denominator, because the size of the building block was 1. So I'm going to just do the numerator part. That's going to be a t minus t squared by 2 going from 0 to 1. And if I do that, I'm going to get 1 minus a half. That's going to be equal to a half. That is my c1. In the same sort of way, I can work at C2. C2 is the inner product of x with phi2, and that's going to be over phi2 with phi2, which, that thing is also equaling to 1. Phi2 times phi2 is just 1 over the interval 0 to 1, and if I integrate 1 over 0 to 1, it just gives me 1, so it's also size 1. Now, the inner product of x with phi2, if you remember x looks something like this, right? Phi2 looks something like this. There's a little piecewise function. So I'm going to break that integral that's related to the inner product of x with phi2 into two pieces. I'm going to have an integral from 0 to a half. That's where phi2 is equal to 1. So I'm going to get 1 times x. That was what? That's going to be a 1 minus t times 1. That's just going to be a 1 minus t dt. And then in the second half, from the 1/2 to 1, that's where my phi2 is minus 1. So I'm going to get minus 1 times 1 minus t. I could write that as a t minus 1 dt. If I go ahead and calculate that out, if I calculate that out, I get a t minus t squared by 2 from 0 to a half, and I'm going to add to that, and I'm going to have in here a t squared by 2 minus t going from a half to 1. If you do the substitutions on all of that, what you find out is you get a 1/4 on there. I'll let you do the algebra. So what do I get in the very end? We're almost done. I get x hat 2 of t, which is equal to c1 phi1 of t plus c2 phi2 of t. Well, c1 was a half, so I'm going to get a half of phi1 of t, and c2 was a quarter, so I'm going to get a quarter phi2 of t. If I plotted that out as well as my original signal, I think I'm going to start getting an idea of why this works and why it was a pretty good estimate. So I'm going to be going from 0 to 1. Let's go ahead and put in my original signal. So my original signal went from 1, right, down in a linear way until it hit 0 at a value t equaling 1. T equaling 1. So that was my original signal. Now I need to add my two basis function pieces together to get my estimate. I'm going to go ahead and call that estimate x2 of t. I'm going to show it in red. First off, what was phi1? That was just a DC value 1. We're multiplying it by a half. So I should get, for the first piece here, a little DC value from 0 to 1 that had a value of a half. To that, I'm going to be adding, right? I'm going to add to it a signal that looks like phi2. There's my phi2. But instead of having t kites of 1 and minus 1, because it was weighted by a quarter, I'm going to get a quarter and minus a quarter. So I just need to add those two pieces together. A half plus a quarter, so I'm going to come in here. There's my halves. There's 3/4. There's a quarter. So a half plus a quarter going up to a value of 1/2. A half, right, plus a quarter is 3/4. So up through a value of a half, right, I get 3/4. When I get down to the next half, so going from a half to 1, I'm going to have a value of a half minus a quarter. That's going to be a value of a quarter. So I'm going to get that guy. And if I just wanted to kind of put it all in there, I could do something like this. Okay, so that red line, right, is my x hat 2 of t, and I think I forgot my hat over there. Is that a pretty good estimate of my other signal? Yeah, it's a pretty good one. It's the one that minimizes the error of the difference when all I have available are those two Legos, those two building blocks, phi1 and phi2. I think that's more than enough for today. We will pick up next time with the formal proof of the orthogonality principle, really demonstrate that the orthogonality principle delivers what it says it does.